it's the time. Anyone who shows up late will be late, and they'll get to see what parts of the talk they see.
All right.
So I suppose we might as well get started. So, hi everyone. I'm Krzysztof Derniak, and this is my Qualls talk. We're going to be talking about Swizzleflow, a system I developed for modeling and synthesizing the irregular patterns of data movement seen in optimized kernels on mathematical accelerators. And this is work I did with my advisor, Ross Bodick, and also the new pruning methods we use to make this synthesis efficient. Now, these accelerators are things like GPUs or vector processors such as Qualcomm's HVX chip, or just the CMD instructions on a typical Intel machine. And these accelerators allow you to get better performance on mathematical operations like matrix multiplication or convolution that are used in lots of domains like machine learning and vision and scientific computing. But in order to gain that performance, you have to stay within the constraints of the hardware. Many of those involve constraints on how memory can be moved around. Like on GPUs, to get best performance, you need all the threads in a group of threads that are executing the same code to load data from the same block of memory, or else your code will be significantly slower. And there's also accelerators like FPGAs that have lots of parallel memory banks, where if you don't distribute your loads across those banks, you will end up with much worse performance because your compute units will stall. And similarly, you can have cases where the hardware offers particular operations or sort of expects certain data layouts. And if you can get your data into those layouts, then you get a lot better performance. Like on the HVX processor I mentioned, that when you're writing certain convolutions, the processor will produce outputs to, say, multiplications in a format where there's a register with the results from the even numbered inputs and one of the odd numbered inputs. And you can take advantage of that fact to sort of slice and dice these registers and order to do the rest of your filter without having to unpack things and write them back to memory and actually use a sliding window. And this is something that experts could figure out how to do, but compilers like Halide couldn't, which is why the handwritten version that's illustrated on this slide is about twice as fast. A more dramatic speed up comes from transpose on GPUs, which is an example I'm using to illustrate how Swizzleflow works, where the obvious approach of just loading your array in a transposed way is about 45 times slower than this more complicated algorithm that uses these swizzles, which are these irregular patterns of data movement you see specified on the right, where the data is loaded in a way that meets the GPU's constraints, and then we shuffle it around within and between the threads in order to actually compute the transpose. And this is pretty helpful in things like graphics programming and games code. Now, this algorithm here is something we synthesized in our previous work, Swizzle Inventor synthesized, and that it's an improvement over an algorithm from 2014 that loaded the data in order instead of swizzling it at the beginning, which meant more permutations within registers. Also, on a meta note, if anyone has questions, please just interrupt me. I won't see your hands. And so that algorithm is something we can model in our Swizzleflow language, where we abstract away a lot of the core details of how the hardware operates and instead can just describe the patterns of data movement in a functional style like you see here in the Swizzleflow code on the slide. We're just describing how the data is moving around. We don't need to worry about threads and things like that. And because of this model, we can represent swizzling kernels from different accelerators in the same language. And we can then do synthesis over with those kernels to find swizzling patterns when the programmer doesn't quite know what they are yet. And they have a general idea for how their algorithm will go, which is the program sketch, where it's like load the data from memory and then it gets moved around between threads somehow. And a mathematical specification like convolution is just say x1 plus x2 plus x3 and so on. And we synthesize a solution to that sketch that meets the specification with the help of our viability tests that allow us to notice that a partially synthesized program cannot be part of, cannot be completed to become a solution. For example, you can observe that certain values are in places that they couldn't come from in a correct program. In a way that I'll explain more later. Yes? I thought I heard someone say something. And I'll discuss sort of what these tests are and how we derive them later. But because of those viability tests, we're able to have a highly scalable algorithm that solves a lot of benchmarks in seconds for in smaller cases and a minute or two in larger ones that can skip 99.6% of the search space and on average, and will also significantly outperform previous work by orders of magnitude. Now, with sort of that general structural
can I interrupt for a
go ahead
question for my intuition as we go forward?
Yes,
so
please.
I certainly imagine how so if I have a 4x4 and I understand it can be larger, let's just consider 16 factorial intractable. Okay.
Sure.
But can you give me an intuition on how many of the permutations are optimal solutions or lead to the faster algorithm? Is it literally one, or are there usually some some rotations that work?
It depends on it actually depends in these transpose problems. It actually depends on the dimensions of the matrix. In some cases, you have sort of a series of rotations that are all solutions. In a few cases, you have like exactly 2 or 3. This depends on the matrix dimensions. And one of the reasons I've been using 4x4 is that for the problems that are like things like 32x4 are ones where you have sort of some interesting permutations, and that's actually is one of the cases where you see rotations of the same algorithm also be correct. But if like if I was using 3, there'd only be like 2 solutions from the set of permutations we're looking through, which is a subset of the whole thing in a way I'll discuss when we start talking about the synthesis. Does that help?
Yes, thank you.
Okay, cool. So moving on, and thanks for the question. Let's sort of talk about how we modeled that transpose code and how we got to that model. So we can see here that the naive transpose algorithm is a description of matrix transpose. But on a GPU, for efficiency, we need to run code like here that's shown here at the bottom of the slide, where you have all these things like this shuffle sync instruction that lets threads sort of broadcast a value and then also read a value that some other thread is broadcasting and things like this. And I think, as I mentioned in response to Dan's question, in reality, this code runs on 32 threads, but we're only going to draw 4. And that 4 is kind of a nice example of an interesting class of solutions. So that's why I went with that one. Now, that GPU code has a lot of these GPU-specific things in it, but we can abstract away some of that execution, and we don't have to sort of really reason about the fact that this is running on multiple threads or that there's this shuffle instruction. We can talk about this code by just looking at it as moving around things in 2-dimensional arrays, where we take our original variables and we add another dimension to represent what used to be threads. And this is still the same general pattern of behavior, but now we're looking at this at a higher level, more abstract fashion, which makes it a little bit easier to think about and reason about. But we don't even need those loops. What we get if we, instead of having those for loops, we just look at this as a functional program in a data parallel type style, we get Swizzleflow, where the fundamental operation is taking data in arrays and moving it around using various functions that are not necessarily permutations, but in many cases are. And that is that's basically what we get, is this model of this code that's just talking about arrays and moving things around arrays. And that allows us to represent lots of different things from different platforms. And now we just don't have to think about the exact details of our algorithm at all, just the core of it, which is the data movement, which you can even see in this kind of figure where we just have the data moving around, and edges are the various functions that control where data comes from. And I'm going to be using figures like this a bunch and explaining the synthesis and viability tests. So I just wanted to establish what we're looking at. And so all of the functions in this Swizzleflow program are gathers, where each element in the output array is defined either by reading from some input array, some particular fixed element from an input, or one of the two special values, 0 and bottom, which are respectively the identity and the sort of undefined or null value. And these gathers can't have dependencies on the values of their arguments, so you're not going to have things like if xi is less than 0 as part of your function definition. In general, you're looking at things like the f I showed on the slide, and in practice at things like the permutation I cropped out of the full transpose execution. And these allow us to represent most aspects of Swizzle kernels, including things like broadcasts or communication between threads or certain conditionals like selecting which value to send, things like this. And because these are generalized permutations but are still easy to analyze. And one note is that in Swizzleflow, all arrays and sort of all function arguments have a fixed shape or type that's a constant, so we don't handle arbitrarily large inputs because the swizzling kernels usually don't, or at least the parts of them that people want to optimize don't. And so we restrict ourselves to these smaller types of to just fixed sized programs, which helps with analysis and synthesis. So in the synthesis case, if we're in a project like, say, Swizzle Inventor, the synthesis we want to perform involves some GPU code, like here at the top, where we've taken the swizzling expressions and replaced them with sort of unknown expressions that are functions of the thread ID and the loop iteration and the bounds on those two variables. And of course, that we want to fill in those expressions in such a way that when the program is run, it has the same behavior as the specification, which is the definition of transpose. And this has the solution that we've been seeing this whole time, where we fill in, or one of the solutions is the swizzles that we filled in here. Now, in the Swizzleflow context, we're looking at a slightly different way to express the sketch, where what we do is we take our concrete swizzling functions and replace them with a set of functions, like how to swizzle rows on a GPU, within rows on a GPU, or within columns. And we want to choose a function from each of these sets such that the program as a whole meets the specification, which is now given in terms of these mathematical symbols, like the first row of our output should be x0, x4, x8, and so on. And that is now what we're trying to synthesize. And again, the solution's here on the bottom. This is still the same synthesis problem, just expressed rather differently. And
Christoph, can I interrupt for another question? I could have asked this earlier, but it didn't hurt me to wait until now.
Sure.
Transpose is, of course, computation free, right? There's absolutely no computation being done. Should I think that in more sophisticated examples, there would be computations, in between these stages? Or should I think that, no, I'm going to do my full swizzle, even multiple, all the steps you can have on the slide, then do some computation, then maybe do another swizzle?
A lot of the times this sort of, you'll see this a bunch when you get to the convolution example. Because we do handle that case, and that's a good question. A lot of the times, kind of when you've unrolled all the loops and things like this, you are seeing that there is computation happening, but you can almost think of it as happening at the end of the program in our representation. Even if when you're looking at loops, you're adding, like, accumulating things into some output or things like this. So yes, there might be some computation, but I didn't want to make the first example too complicated.
Right. So, and that's fine. And I don't want you to switch to a more complicated example. So there are things like convolution where you can think of the computation happening last, but maybe there are other more like stencil-like things where maybe you can't. Or should I just have the intuition of I'll do computation at the end?
Well, some computation you can do in the middle. It depends on what you're thinking of exactly, but this sort of swizzling language, kind of once I introduce how we handled the computation, can probably handle a lot of things that with stencils and I think polynomial multiplication we could express and things like this. So you can have computation in the middle between various different types of swizzling. So just as sort of our notion of computation is somewhat restricted to make things behave. But that's a good question.
Thanks.
All right. So to get back to things, what we're looking at is the set of functions that we're trying to choose from for these GPU swizzles, which were defined in Swizzle Inventor. That most of the expressions people tend to use when swizzling data are formed from a fan composed of a rotation with optional grouping in the middle, as illustrated in these pictures. And in Swizzle Inventor, they had to often do things like disable grouping in order to make a lot of their larger benchmarks synthesizable, and we've removed that restriction. But also, this is specifically the way we handle swizzles on GPUs, because one really platform-dependent bit of Swizzleflow, other than what the different array dimensions mean, is what goes in the holes. Like on HVX, we can actually represent the native swizzling instructions on that processor with gathers and synthesize over those. But this is, when we're doing the search, these are the kinds of functions we're looking at for the GPU-based examples, which are most of this talk. Now, the synthesis is an enumerative search where, as always, just kind of going through and executing the program and picking value for each hole, backtracking, etc. We could, in principle, have done some kind of statistical approach, but it turns out we didn't really need to, because our viability tests work quite well for most of the cases, in just about all the cases. So what I'm getting at is that if we look, is that while in sort of a practical example, like a 32x4 transpose, you might have 10 to the 13 paths about, and that's just infeasible to enumerate. When you're looking at some of these intermediate nodes in the search tree, you can observe that it is not possible for them to lead to a correct solution based on what you know about what's left in the sketch. For example, that value for S1 on the left of the tree can't be correct, since it just resulted from loading the diagonal of the input over and over again. It doesn't have any copies of the value 1 in it, and so we can reject that state as it's not all leading to a solution, because there's no way in the rest of the sketch for the value 1 to be reintroduced. And the more complicated case is that value for S2 on the left, where if we look at the 1, it's in the wrong row. And we know that with the remainder of the sketch only being permutations within rows, a value for 1 that's in the first row cannot be, the value of the one that needs to be and the second row in the output cannot come from the first row of S2. And so that conclusion, just about looking at the value 1, allows us to conclude that that value for state for S2 is incorrect. And these are all turned upside down because we're sort of reasoning from the specification backwards. Now, that type of reasoning, we're looking at individual values and where they can come from, is an approximation to correctness, of course, in that if we look at the value for the value 5 can move, we know it can come from anywhere in the second row, which of course it does in the correct solution, but also in this incorrect solution on the right, where the 5 could move to the correct place, but for example, the 15 is in the wrong row. So we'd, at the very least, have to look at all of the values, and this will still, even in that case, potentially be an approximation to correctness. Now, the way we actually draw these types of conclusions is by pre-computing this kind of reachability data, just looking at the locations in these various arrays, without just looking at the sketch without knowing what the specification is yet. We can conclude, for example, that the value in index 10 of S3 has to come from the second row of S2. It's the only possible way for that to happen with our sketch. And in fact, because that sketch includes just rotations, it can come from any location in S2. And by taking this pre-computed reachability data, we can overlay it, or the specification and a candidate state, and notice that for example, the output in index 1, 0 has to be 1, but in the incorrect state, there is no 1 in the places a 1 would have to come from, while there is a 1 in that row in the correct state. And if we perform this kind of analysis for every value, we can draw useful conclusions and reject incorrect states. Now, the problem here is that if we just look at one location, this is not particularly useful, as shown here on the left, where we are looking at when applying row swizzles and then column swizzles tells us that that output where the 1 needs to be can come from anywhere in S1, which is not very useful information, almost doesn't allow us to reject almost any values of S1, which is why just tracking one location caused all of our benchmarks to time out. So what we instead need to do is look at a pair of output locations and ask where can those two locations come from simultaneously, and that the value 1 can come from one of these places while value 2 also comes from one of these other places. And this it turns out to be sufficient to, again, reject 99.6% of the search space and to let 45% of our benchmarks be prune as optimally as an oracle that would just tell us whether a state is in a solution or not. And you might be wondering if, since tracking 2 locations works quite well, what happens if we track 3 or 4? The problem here is that tracking 3 locations or more than that causes the data we're computing to be too slow to create and too large to meaningfully store, at least with our implementation. And we don't yet have any interesting ways to sort of selectively refine the abstraction with how we've defined it, even though that could be an interesting direction. Now, all of this reachability analysis of what locations, or since we're in some sense what variables can this pair of output locations come from, is a data flow analysis that's somewhat related to things like taint analysis that has a few useful properties. One is that because Swizzleflow requires the arrays to be of finite size, the set of pairs of locations we're tracking is of finite size. And similarly, sort of how each function behaves on each pair of outputs depends only on that pair of outputs. And there's not sort of any other interesting interactions within the program that allow us to conclude that the transition rules for how we draw conclusions about the inputs to a statement from how its outputs behave distribute over sort of the union in terms of what variables we know a particular output pair can come from. And finally, the solution is a subset of variables in this case. So that makes this entire problem expressible as graph reachability per the results from reps back in the 90s. And specifically by taking each program statement and exploding it into one node per pair of locations and drawing the edges between them based on how those locations can move around abstractly. Now, what that looks like in practice is that we can take a set of functions, like the one we drew here, and represent it as a statement matrix where we record sort of how things can move, where things could have come from for any particular pair of output locations. Like here in this matrix, we see that you can flip the 2 outputs around, but you couldn't, for example, have this set of functions can't duplicate one of its inputs, for example. And we compute one of these matrices for each statement, which is a function or a set of functions in the sketch. And then starting from the output of the program, we can multiply these together to get the reachability to each pair of output locations simultaneously. And we do this simultaneously because the graph structure for this reachability is always the same, no matter which pair of output locations you're interested in. So you can compute them all at once with matrix multiplication. And what's extra nice is that these are Boolean matrices that are quite sparse. On the GPU benchmarks, all but 2 of them, all of these individual statement matrices had less than 5% of their bits set, and 82% of them had less than 1% of their bits set. And these are quite large matrices, like millions of entries, for example. But even still, while composing these matrices doesn't necessarily preserve that sparsity, because, for example, if you're swizzling within rows and then within columns, that allows you to do many more things if you do one after the other than each of those 2 sets of functions individually. But with that, the fact that one of our matrices is sparse and that they're made of booleans means that we can use specialized algorithms for that multiplication that on, say, a 32 by 5 matrix transpose allows us to multiply these matrices about 0.08 to 7 seconds each, depending on how sparse the matrix is, versus if you just use dense floating point matrix multiply, which is the obvious first tool, then that takes about 2 minutes each and is much less practical. So now to kind of get to Dan's point about more complicated examples, let's look at convolution, where most of us know the specification. Take each output is the input plus its k neighbors off to the right. But again, on a GPU, there's a much more complicated implementation of this that is faster than the naive version, where you take your input data, you load it onto the registers of multiple threads, and then you have those threads sort of send different values on different loop iterations so that every thread gets the values it needs and then adds them together to get it produce its final output, as you see sort of in the picture here on the right. Now in Swizzleflow, we take that loop and we unroll it, and now we have arrays representing things like the 2 values each thread loaded and which value it decided to send and which value it received. But more importantly, you have this fold operation, which we can use to represent the reduction aspect of this computation that is new and we didn't see in the transpose. And fold effectively takes the those values that were received and packs them into something like 1 plus 2 plus 3, which is the actual output, so we don't have to care about which order the values arrived in. And more kind of formally and generally, these folds can represent any reduction that you need, addition, multiplication, maximum, things like this, and anything that's associative and commutative and has an identity. And the order of elements you pass into doesn't matter, because what fold does is it takes the last dimension of its input and it packs it into these multisets, as shown here by the sort of formula for fold. Fold also ignores zeros, so we have an identity element, which also allows us to implement things like conditional accumulation. Add something to the output if it's a certain loop iteration, or and of course empty fold is 0. And one note is that nesting these folds represents multiple different operations, say multiplying things and then adding some more stuff to them, and does not represent parentheses. And so fold of A and B and then C is not the same as fold of A, B, and C. That's a kind of useful note about just our representation. And
sorry, Christoph,
yeah.
Apologies if this is just syntactic criticism of your slide, but
yes,
you don't seem to be representing which operation is going with which fold.
Yeah, that's a valid syntactic criticism of my slide.
Okay, but in practice, you say I want to fold plus over the following set of elements, right? I'm happy to mentally insert the operation on the slide.
Please do mentally insert the operations. My language implementation doesn't currently keep track of them explicitly, but that's not inherently the fact that I don't have that isn't some inherent requirement of this system. It's just
and it may even represent that you don't actually care which operation you're folding across.
Yeah,
but when I'm learning the semantics of these examples,
no, I agree, and I agree, and that's an oversight on my part. Thank you.
Not a problem.
I'll fix it in the paper. Actually, let me just note that down real quick, just so I don't forget about it. I mean, I can't edit in here. Never mind. But no, thank you. But the claim is that these two types of operations, gathers and folds, will allow you to represent most of the behavior you see in swizzling kernels, because these kernels generally don't have arbitrarily large inputs. So we don't have to represent those. If there is an arbitrarily large input, there's usually some outer loop that just chops them into smaller pieces, and then the fixed size part is what gets heavily optimized. You also don't see dependencies on the inputs, things like if xi is less than 0 in these types of code. And finally, there's typically not loop carried dependencies that aren't these kinds of reductions. And so we can get away with unrolling all of our loops into an array dimension sort of that represents time in the same way you see in a lot of polyhedral compilers. And now this does impose some limitations on the kinds of code we can synthesize. One is that we can't handle data-dependent indexing, so we can't deal with sparse kernels, but those are a much more difficult problem that we don't not try and tackle in this work. We also can't deal in things that have lookup tables or otherwise require bit accurate reasoning for proving, kind of describing how they work, like the inverse square root that we found in the HVX SDK, which we can't do because that has just a big table in it. And similarly, because of how much we've abstracted out how arithmetic works, on HVX, they have a bunch of different arithmetic instructions that you might want to choose from that we currently just don't have sort of in the Swizzleflow model, can't actually select which arithmetic instructions to use. We could add a search for that, but the model itself doesn't really express this. Now, when we're synthesizing convolution, we of course can, same as before, take the swizzles, what gets sent on which iteration and where each thread reads from, and replace them with appropriate holes, one of which is sort of Boolean valued. But there might be a problem here, which is that our specification is in terms of things like 1 + 2 + 3, but earlier in the computation, we're only going to have 1, 2, and 3, and we won't. So if we're saying that some term, where can 1 + 2 + 3 come from? Well, we don't know. There is no 1 + 2 + 3. So what we do instead is we start looking for subterms of the specification that appear in kind of a correct place in the intermediate state. Like here, we see that the first output is created from the first row of received, and while in the incorrect program on the state on the left, 2 and 3 are in the correct row, the 1 isn't. So that state is incorrect and we can reject it, while the state on the right is a potentially correct one. And so that's sort of how we solve that, but we don't always go directly to the basic terms, where if we're looking at, say, a convolution where the user has passed in weights as a parameter, what we can do after we've actually executed the multiplication of data values times weights, then we can start checking for whether, say, x1 w1 can come from somewhere or x1 w2 can come from some appropriate place, and if any of those are missing. But before that, we just look at x's or w's as necessary. And even in the case of multiple arguments, say maybe we want to parallelize part of the search, then we can, we know that sort of the variables containing data won't contain any weights, so we don't accidentally reject the correct program by looking for weights in the data variables. We do this by getting a universe analysis that tells us what terms a variable might contain, and kind of approximating what could be in there. And we can just look only for the subterms that are in the universes of the variables that are currently live, also as the ones that might contain terms that we're interested in. And so that's effectively how we handle the problem of doing this reachability analysis with kind of reductions and computations and things like that. And so, and also with multiple different arguments. But we did have to add one more viability test to make certain benchmarks work properly. That's the copy count test, which is probably best illustrated by a straightforward sort of scalar example, where our synthesis problem is that we want the output to be a plus b from adding x plus y plus z, and x, y, and z are either, could be 0 or they could be a or b depending on what we specified. And if we're searching along and we say x is equal to a and y is equal to a, then that program can't be correct because the output will definitely have a plus a in it, which is not really compatible with a plus b. But the reachability analysis will just look and say, oh, where could the A in the output come from? It could come from X, it could come from Y. Okay, both of those seem fine. And so this reachability analysis, one of its limitations is that it can't detect extra values. And this is actually a problem on a few benchmarks in practice, like in polynomial multiplication, where we're trying to synthesize when to add things to accumulators. So we're trying to selectively replace values of zeros. And there's 16 of these conditionals we have to synthesize, but 8 of them need to synthesize to false. And the problem is if we just have the reachability analysis, then every single value for that conditional will be considered potentially valid because it's like the correct program, just with some extra stuff in it. And extra stuff is fine for its reachability purposes. So the solution to this, which gets the search time on this benchmark down from timeout to 3 seconds, is that for every location, we compute lower and upper bounds on how often that location can appear in just the entirety of the output by, again, sort of working backwards with the program. And then for every term that we're currently interested in, we take those bounds for every location that contains that term, add them up, and see if the actual true number of copies lies within the bounds. Now, for example, on the scalar program, we'd say X will appear once, Y will appear once, and those both contain A's, but 1 plus 1 is 2, which is greater than 1, the number of A's we need. So we can reject this partial program by looking at copy counts. And yes, oh, I thought I saw a hand. Like, oh, the corner of my eye. Anyway. So with that, I think that kind of summarizes how the system works. Let's talk about the empirical results, where we evaluated Swizzleflow in 3 ways. 1 is how scalable it was, 2, how effective the pruning was, and 3, how we did compared to Swizzle Inventor. So on the first question of the scalability, most of these benchmarks that we attempted for GPUs, we could synthesize in seconds for the smaller problem and a minute or 2 in sort of larger cases. That Gaussian kernel that I was showing as an example, I could synthesize in 0.6 seconds. Now, while these graphs overall do show this sort of polynomial relationship, there are some cases where the larger benchmark is faster, and that's because in between different experiments, we can cache these statement matrices for each whole, so that if multiple different programs use the same set of functions, then we can just reuse the information we computed about them, and we don't have to rederive it again. One note just also is that all these charts refer to Trove, which is this matrix transpose problem where there's a couple different variants of it. CRC is column row column, it's the one from 2014, and row column row is the one I've been using an example this whole time. And sum is one where we take, instead of actually transposing, we add the results together of the, just gonna need to sum over the transposed matrix. And in all these benchmarks, we searched for all solutions. This is 1, to keep the results deterministic, and 2, because we don't have a cost model in our search. And Swizzle Inventor did, even though it was a somewhat trivial cost model, we still wanted to make sure we were being fair in case, say, Z3 was taking advantage of that cost model. So now there are some limits to our scalability. The main one is running out of memory. And that is, for example, the fact that if I try to do a 32/11 transpose or a convolution or stencil with width 15, over 32 threads still, then those matrices get so large that they won't fit in the 16 gigabytes of RAM on my laptop. And so we can't synthesize those. And there's couple other cases. One is that in a 11/11 filter, you need to synthesize sort of 3 conditionals like this simultaneously, and actually constructing that set and constructing the statement matrix for that whole causes us to time out. And there is one benchmark where we run into limits with our abstraction, and that is a variant on the polynomial multiplication where the data comes from shared memory, and not by being loaded in registers. It takes us an hour, which is above our timeout, and of 30 minutes. And this is the one benchmark from Swizzle Inventor that we couldn't solve with our approach. As to why, I'll discuss that when I talk about the effectiveness of our pruning strategy, where the main metric of interest is how well we did compared to the best possible pruning strategy, where we would only explore states that could appear in a solution. And we just have the oracle of is this state a part of a solution or not. 45% of our benchmarks actually pruned as well as the oracle, and a lot of the ones that didn't came close, like the transposes or a 7x7 stencil that have were about 1.01 times worse than the oracle. There are a few cases where we do noticeably worse. One of the ones worth mentioning here is a 1D convolution, where in this case the convolution benchmark actually had the weights passed in as a separate argument, as I showed in the universe slide. And when we have that, there are two solutions that have each have their own way of swizzling the data and then correspondingly swizzling the weights. So there's two ways to swizzle the data that are correct and two ways to swizzle the weights that are correct. But only out of those four combinations of swizzles, only two of them actually lead to a solution. The other two are incompatible with each other. And with our abstractions, we can't really detect that until we actually try to combine the data with the weights. And that's why we're doing about twice as worse as the oracle that would know about that incompatibility as soon as we started. Now, this actually gets us even more on the polynomial multiply benchmarks, especially the large ones, where there's tens, hundreds of ways to swizzle each polynomial, most of which are incompatible with the way we swizzled the other argument. Then there's two polynomials we're multiplying, and most of the ways to swizzle those are incompatible when we combine them together. That's actually why we time out on the shared memory benchmark, is because we have hundreds of thousands of states to filter through, and only a few of them actually correspond to solutions. Now, the HFX Gaussian actually runs into a different problem, where at the beginning of our search, the reachability matrix is concluding based off of that with 5 or 6 different swizzling instructions, approximately anything can come from anywhere. And so we have to enumerate 1 or 2 instructions before we can begin meaningfully pruning. And this does show that eventually, if we stack up enough of this sort of pair reachability data, it stops being useful. But even with that, we had quite good performance. Now, another interesting fact, so I show what's going on with pruning, is that our search times are just about negligible. They're almost always less than a second. And kind of see that on the fact that almost none of these pie charts for the large benchmarks actually have any visible red on them. And so most of the time in a Swizzleflow execution is spent computing and multiplying together these various reachability matrices that, the variance between computation and multiplication sort of depends on the problem and how much stuff is already in cache. But this really shows the effectiveness of our viability testing and pruning methods, and also the fact that these circles aren't solid green shows the usefulness of our Boolean multiplication. Now, if we look at speedups compared to previous work, we have dramatic speedups over Swizzle Inventor in the case where we're using sort of the full unrestricted grammar of swizzles. Or we have sort of 10x, even in the case of stencils, 1000x speedups. And in some cases, we had solutions to benchmarks they timed out on, like a 7x7 filter using this full grammar, which is why I've drawn in infinite speedups. There are some cases where we have much more comparable performance, like some of these transposes where there isn't a solution. We can both prove the lack of a solution rather quickly. And in general, as I said, in Swizzle Inventor, they had to restrict their grammar to make a lot of these larger benchmarks feasible, and we didn't. So that allowed us to sort of explore a wider space of algorithms with our approach. And A main reason for that is that pre-computing this viability information, looking at pairs of values, it turns out to be faster than having the SMT solver rediscover properties of the grammar and what can and can't be part of valid solution every single time. And there are a few exceptions to this, namely, especially once we bring in that restricted grammar, that Z3 can find things while we're still multiplying together matrices. But in both those cases, we're looking at 1 or 2 seconds of search time. So this is extremely interesting. It's not major, but it is worth pointing out that there are a few cases where the Swizzle Inventor approach is better. And one other reason that we're seeing these speedups, especially on the unrestricted grammar, is that we're looking at sets of functions, whereas in SMT synthesis, you're looking at finding an expression in a grammar. And in the Swizzle grammar, there were a lot of expressions that were syntactically distinct, but had the same semantics. And so the fact that we're looking at a set of functions means we only explored each of those expressions once. And so we broke certain symmetries in the grammar. There is a good amount of related work on this topic, but most of it's going to be in the report. There is a paper I'd like to mention, though, which came out at this year's OOPSLA. That is on dataflow-based pruning for superoptimization, where the problem they were trying to solve was finding the best expression for some small fragment of C code or LVMIR code and they wanted to be able to enumerate the expressions while observing that a partially instantiated expression might just be impossible. Like they could analyze data flow between various bits to show that a left shift cannot optimize x plus 1 or 1. And it's quite a nice paper, and I would recommend it. I'd like to thank several people for their help with this project. Ross Bodick, my advisor, for lots of advice and feedback and pushing on this implementation to simplify it. Sam Kaufman for being a rather helpful sounding board for all this. And Maz Ahmad, who is unfortunately not here right now, who has the HVX hardware and helped me get performance numbers and a lot of the benchmarks. And An Wang, who is an undergrad who graduated from about a year ago and who was helpful in getting a better characterization of those transpose solutions. So we had more benchmarks to look at as we were starting out this project. And with that, just to summarize, there's these mathematical accelerators that need swizzles in sort of the inner parts of their highly optimized mathematical code to get performance. And we've developed Swizzleflow, a model of this kind of code that lets us represent it in a high-level way that we can then use to perform synthesis over these swizzles. And programmers just provide a high-level sketch. And this synthesis is efficient because of the new viability tests we've developed that allow us to obtain significant speedups over previous work and have a highly scalable algorithm. So I think with that, I will take the questions at the end. Thank you.
Thank you, Krzysztof.
Thank you for awkward Zoom applause. I appreciate it.
Let's open the floor to questions to people.
Yeah, who's in here anyway? I can't actually see the entire. Let's see if I can see who else is in here. I'm now curious as to who showed up.
Sam and Chenlong is here, as well as Julie.
Oh, okay.
And, your family is here.
Okay, yeah, there's various people here. Okay, I just clicked this arrow to see more people. All right, cool.
So I'll start with a question. It looks like Sam was about to, but let me give this one question. It's on the empirical side.
Yeah.
You pointed out that in some larger benchmarks, these abstractions are not very useful for pruning, perhaps because they saturate.
Yeah, they saturate the, yes.
Meaning, so what does saturation mean? And what are the causes of the saturation from what you have seen?
So the main space I observed it in was on the in the sort of HVX synthesis context. And the general causes of saturation is that when you have a sort of, especially if you have sort of a set of very expressive set of operations that can move data from lots of different places to lots of other different places, then once you start composing these things, either with themselves or with other similarly expressive operations, you will potentially see a case where sort of things compose in such a way that a pair of locations in the output could come from any possible pair of input locations. And sort of with the sort of HVIX swizzles being things like, take any two registers and kind of cut and paste them into each other according to some constant for how much comes from which one. And you do enough of these kinds of operations in succession, and you find that you can get a pair of values from any of your initial inputs to approximately anywhere, or at least that you could fix. If you make a mistake initially, from the perspective of the abstraction, you could fix it later. And even if you necessarily can't. And so that sort of represents, that kind of saturation sort of represents the fact that you don't eventually sort of stop being able to draw meaningful conclusions just by looking at a couple of values and how they move.
So is there a solution you could recommend for that particular HVX example where these instructions are too expressive?
So one potential solution sort of, I think, could be something like what was seen in the GPU case, where you take your instruction set and you split it up into sort of smaller chunks that are themselves less powerful, but compose into something more, something like the original set of expressions, which I think Boz is doing something related in his synthesizer for parts of this problem. But yeah, another potential recommendation, which I think one direction that could be interesting to explore, is whether there's ways to sort of refine the abstraction in sort of for some like subset of the locations, that because there's a lot of work on sort of abstraction refinement and things like this, that since we know that computing triples for everything is going to be somewhat inefficient, but there might be ways to do it in sort of a limited context. There's a couple different possibilities there, but yeah, that's my thoughts on that.
Right, but if those instructions encode all possible permutations.
Oh yeah, okay. If those instructions encode all possible permutations, then you may be a little bit out of luck. Like if you can permute your inputs however you like, then as long as you don't get rid of any, or you just don't have enough, or you just don't have enough room to store all of the inputs you need, which I think is, unless you can draw that conclusion, it's a little bit hard to do anything. So this is yet again the case where in synthesis you have to be careful with what your grammar is. But
thank you.
Yeah.
Other questions? So.
I have a very naive question, which shows I haven't done any GPU programming at all, including of this sort. But I do know that in a lot of more traditional high-performance matrix computations, there are issues around the edges and the corners, right? And different approaches to how to handle, the leftmost column or the rightmost column, either for uniform operations or for operations that might be, move all the columns to the left and make the rightmost column all zeros.
Right? Oh yeah, true. Or even things like triangular solve, where you have,
So is that handled at a layer below your work? Is it something that your work has a complexity that doesn't come through in the presentation? Like how do we?
The splitting things up into layers like that is handled. I would say it's handled above my work.
Okay.
That's more of a schedule. Basically, if you have sort of separate treatment for most of your matrix and then like the diagonal or the corners, then you might be doing 2 runs of this algorithm, one for each of those kernels, because they're solving different problems.
I see.
But yeah, that's in some sense a scheduling question, which I think one of the slides I didn't have in here kind of pointed out. There's a lot of work, things like auto TVM, Lyft, that are doing quite a good job of, given this large operation, how do we break it down into small pieces?
That's interesting. And saying, oh, it's above my work, you would, use my work a small number of times in order to handle those different regions is a perfectly sufficient answer. But it does seem something within the realm of synthesis as well, because it seems like there's sometimes a small number of choices. One is to condition on what column you're in. Sometimes you pad with a ghost column that you throw away afterwards.
Right.
There's sort of a set of known techniques here.
Yeah, agreed. And I think that's actually there's sort of a project that Sam and Ross and Moz and I are working on that's trying to do some of that synthesis for the rest of the other layers of the computation. Sort of being able to synthesize things for an entire neural network or things like that. So it's a good thought. I'm working on it. We're working on it.
Yeah, you can even imagine, and again, that there might be some algorithms where a particular region, let's say a particular column, although I don't know that it would necessarily be a column.
Sure.
Could go with either part of the algorithm, right? For that column, you can do it the same way as the stuff to the left or the stuff to the right. And which way you choose might affect how efficient your swizzle is.
Okay, yeah, that's all right. That's true.
Okay.
I can't think of any examples off the top of my head, but I could see that. Yeah, how you break down the boundaries, and I could see that being a concern. I'm not trying to sort of be the be all end all of synthesis. I'm still expecting that's human experts to be in the loop on this.
Yeah. Because
I just sort of want to help out the experts with the tedious details of their programs in some sense. With those, that's sort of the limited scope of Swizzleflow in particular.
Thanks.
But yeah. More people? Is it time
no other questions? I'm sure there
I have one, but only if nothing more urgent is on the docket. You mentioned earlier that you had sort of an idea for how you might compose instructions as a way of dealing with the saturation issue. I was just wondering if you had an example. I wasn't totally sure I followed.
I mean, the sort of example I'm thinking of is the fact that, for example, we like in the GPU case, we could break things down into fans and rotations. And sort of maybe on like HVX, you might sort of want to kind of pick, say, via lines followed by some other type of swizzle instead of having those all be in one box.
Okay, I see. Yeah.
Because that one box is sort of more expressive, and you might get more accurate information, or at least be able to reject states faster if you've split. Even if it doesn't fully solve the saturation issue, you at least get more chances to reject something if you've sort of split your set of choices into a couple smaller bins that you then do pruning in between. I guess is a more accurate statement of what I was thinking there.
Okay. Thanks.
Yeah, no problem. I'll let the professors decide when to clear the room.
It turns out I was wrong about there being a public versus private portion of the exam. Everything is public.
Oh, really?
So
okay.
We are not hiding any questions.
Okay, I could have sworn there was I could have sworn that when these were being done live, they told everyone there was a point where everyone had to leave, and
this is a common misconception that's true for generals and the defense. Quals, it turns out, is a holistic thing where quals involves your courses and your research and your presentation and your write-up. And so there's no exam aspect to this. This is just a necessary part of the overall process.
Okay.
This confuses the heck out of people all the time.
I mean, yeah,